Hello all, welcome to this video on Microprocessor Lab. Today I'll be talking on how to do a 16-bit addition using an 8086 microprocessor trainer kit. The kit we'll be using here is an STS8086 LCD microprocessor trainer kit. Now this is how the kit looks like. Here the connections J3, J4 and J8 will be used for serial connections. And this is the 5-volt ground connection. And this unit here is an 8259A, which is a programmable interrupt controller. Then we have an 8253C2 here, which is a programmable interval timer. Now this is an octal D type transparent latch. And this is a 3:8 decoder or demultiplexer. This is an 8251 APC, which is a universal synchronous asynchronous receiver transmitter. And this is a hex inverter. Then we have a 5-volt powered multi-channel RS-232 driver and its receivers. This is the RS-232. These two are quadruple 2-input positive OR gates, and then this is the keyboard connector, and this unit here is containing the decade, divide by 12 and binary counters. This is a D flip-flop here. Then we have a reset button, and this is the 8086 unit, and we have an LCD. And this is an 8255 AC2, which is a programmable peripheral interface. And this is an octal transparent D-type latch with 3 state outputs. And this is another tri-state octal D-type transparent latch with edge-triggered flip-flops in it. These two are the static RAMs and these are the erasable programmable ROMs. This is the odd bank and this constitutes the even bank. Then this consists of the bus lines. In that, 2 units here are another set of 8255 AC2, which is again the programmable peripheral interface. Now these are all the components inside the circuit. Now when we look into it in detail, we'll see that this can be used as a developer kit for 8086 based programs and interfaces. It has some key features which are its user-friendly monitoring program and a built-in inline assembler for entering the programs, and it's very simple menu operated commands, and it also gives proper error messages to identify the assembling errors present. Now we look into some of the system specifications present. Now this kit consists of a CPU which is 8086 and which is a 16-bit processor, and its clock frequency is 6.144 MHz. And it has a keyboard support which is a PS2, which is also IBM compatible, and its display is a 16:2 LCD unit. And we have a RAM which is of size 64 KB, that is we have 2 units of 62256. Then we have EEPROM, which is also having a size of 64 KB, which contains 2 units of 27256, that is these two. Then we have the IO lines, which are 48 lines that we already saw, that we have 2 set of 8255 here. Then we have a timer or counter which is 8253 and an interrupt controller which is 8259. We also have the 8251 interfacing unit, and also the bus lines will support the address, data and control lines which are TTL compatible. and the power supply is 5 volt and consumes current of 800 milliampere. Its operating temperature is from 0 to 50 degrees Celsius. Now we will look into its memory mapping. So for ROM, the starting and the ending address is in the same segment, whose address is 8000, and its offset address varies from 0000 to FFFH. In case of RAM, the segment address both for starting and ending address is 0000, and its offset varies from 0000H to FFFH. The user is allowed to enter the program from the location 0400H to FFFH. Then we look into the mappings for ports of other units like 8255. Now for the first unit of 8255, port A is location 40H, port B 42H, port C 44H, and the control word at 46H. Now for the second unit of 8255, port A is at 60H, port B at 62H, port C at 64H, and control word at 66H. For 8251, data is present at A0H and the control word at A2H. For 8253, timer 0 is at C0H, timer 1 at C2H, timer 2 at C4H, and control word at C6H. And for 8259, data word is present at E0H and control word at E2H. Now we will look into the menu commands that are present in this trainer kit. The option A stands for assembly. Here, the user can enter the assembly language directly into the kit, and the assembler will assemble the 8086 instructions in machine code. Now, when we press the A mode, they'll ask for the starting address of the program. After entering the address, when we press the enter key, we will be given a screen where we'll be entering the program. Then we have an option called B, which is block move, which is used to move blocks of data from one location to another. Then we have the option D, which is to disassemble the program in order to examine it. Then we have an option F, which stands for fill data, that is used to fill the RAM locations with a particular data. Then we have the option of G, which is to go or execute. Now it is used to perform execution of the program. On selecting the option G, it will ask for the starting address. On entering it and pressing enter key, the execution will start. Then we have an option called M, which is used to modify or view the contents inside the memory. On pressing M, they'll ask for the address of memory whose content is to be known. After entering the address and pressing the enter button, the screen will show the corresponding address and the content currently present there. So you can either see the content or you can also modify it by typing it the input as hex values using keys from 0 to 9 and alphabets from A to F. Then we have E option, which is used to edit or view the memory. Then we have R, which is used to view the contents of a register or even edit it. Then we have the option S, which is used for single step execution of the program. And we have the option T, which is used to either enable, disable, or modify the breakpoints, if any, that is present in the program. Now 16-bit addition can be done in different ways. Now we will be sticking on to a particular method here. So for this, we will be using the following registers, that is SI, which is the source index register, which will be pointing to the location from where the operands for addition are taken. And we have DI, which is the destination index register, that will be pointing to the destination to where the result of addition will be stored. Then we'll be using the registers AX and BX, which will be the operands for the addition. And then we'll be also using the instructions like move to transfer content from one location to another. And we'll use the increment instruction that is used to increment the pointer registers, which are SI and DI. We'll use the add instruction for adding the two numbers. We'll also use two varieties of jump. The first case will be JNC, which will be jumping based on whether there is a carry or not. Now for JNC, it means that if there is no carry, we'll specify the address of location to which the jump is performed. And we'll be also using the normal jump, which will be followed by the address to which the jump should be performed. And lastly, we'll also use the instruction halt to mark the end of the program. Now we'll look into the program in detail. Now the numbers that are written in blue are the address where these instructions will be stored. So the first statement here will move the value 3000 to SI. That is, the pointer SI will be pointing to the location 3000. Now this instruction has 3 bytes size. So the next instruction will be stored at the location 2003. This statement will point the register DI to the location 4000. That is the place where the result will be stored. Now this is again a 3-byte instruction. So the next instruction will be stored in the location 2006. Now in this statement, the content that is present at the location pointed by SI, which is the first operand, will be stored into the register AX. This statement is of size 2 bytes. So the next instruction will be stored in the location 2008. Since the first number is taken and the data is stored in consecutive locations, we need to increment the index register, which is done using the instruction INC. Now increment will only increment the value of SI by 1 byte. Since we are using a 16-bit number, it will have 2 bytes, so we need to write this instruction twice. Also note that this instruction has size of 1 byte. So after increment SI, the next statement will be written at the location 2009, which is again increment SI, which is again of size 1. So the next statement at 200A. Here we'll access the second operand, which is pointed by SI, and store it in the register BX. This statement is of size 2 bytes. So the next statement will be written at the location 200C. Here addition will be performed within the two registers, that is add AX, BX, and the result of addition will be stored at AX. Now we are checking whether there is a carry or not. Now this statement is of size 2 bytes, so the next instruction will be present at 200E. Here we'll use the jump variant, which is JNC, that is, we jump to a particular location if there is no carry. So JNC followed by the location to which the jump should be performed, that is 2015. Now if there is no carry, then in the space that is reserved to store carry in the destination, we'll write the result as 0. So what we do here is, we'll move the value 0 to the location pointed by DI. This instruction, actually the statement, is of size 3 bytes. So the next instruction will be at the location 2018. Then we'll increment the value of DI so that we can point to the next location where we need to store the result of the sum. This is again a 1 byte instruction. So the next instruction will be stored at location 2019. Here we will move the contents, that is contents of AX, which is the sum, to the location pointed by DI. And this statement is of size 2 bytes. So the next instruction will be written at the location 201B, which is the end of the program, halt. Now we look into the case where there is a carry. So if there is a carry, this statement will be skipped, and this statement is of size 2 bytes. So the next instruction will be written at the location 2010. So if there is a carry, then we'll write 1 to the location pointed by DI, which is written as move the location pointed by DI, comma 1. And after this, we need to take the contents of sum. So we'll perform a jump to the location 2018. This instruction is of size 3 bytes. So the next instruction will be present in the location 2013. And the jump statement is 2 bytes of size. So the move instruction will be placed at the location 2015. Now before going into the demo of how the program is executed, we'll have to note certain things here. As already discussed, 3000 is the location where we'll have the 2 operands, and 4000 will be the starting address of the location where we'll be having the result of addition. So in 3000 and 3001, we'll be storing the lower byte and higher byte of the first operand respectively. Similarly, in 3002 and 3003, we'll store the lower byte and higher byte of the second operand, which is BX. And the result location, which is starting from 4000, there we'll store the value of carry. That is either a 0 or 1, followed by the location 4001 and 4002 containing the lower byte and higher byte of the sum. So in total, these three locations will contain the sum and the carry values. Now we'll see how this program is executed in the kit. We have a keyboard here which is connected through the keyboard connector to the kit, which is STS8086. So first of all, we'll switch on the kit. Then we open it, we'll get this interface where we have the commands, and this is the diagram we have already discussed in the beginning. Now I have to enter the assembly program. For that, I'll choose the option A, which stands for assembly. They're asking me the starting address, which is 2000 in the case of the program we discussed before. Pressing enter, we can enter the entire program line by line. The first line will point the pointer SI to the location 3000. Then we press enter. Again pressing enter, we will get the next location, which is 2003. There we will write the instruction for pointing DI to the location 4000. Then we will move the contents, that is pointed by SI, to the location AX. That is the first operand. Then we need to increment the value of SI twice for moving to the next operand, since data is stored consecutively in this case. Then we will move the contents of the pointer SI to the register BX. That is the second operand. Then we will perform the addition, add AX, BX. Then we will check for the carry and perform a jump if there is no carry to the location that is specified here, which is 2015. And if there is a carry, then we'll write the carry value, which is 1, to the location that is pointed to by the register DI. After that, we jump to the location 2018 where we need to store the code that is the result of the sum. So there what we do is we'll move the contents of 0000, that is the case when there is no carry, to DI. Then we'll increment DI so that it points to the location where the sum needs to be stored. The next statement will be move DI, comma AX, since AX contains the result of the sum. Then we give the halt to mark the end of it. After pressing enter, we will press the escape button. So we'll go back to the initial screen. Now we need to enter the values into that memory location. So we'll give the starting address, which is 3000, and pressing enter. So here I'll be trying to add the numbers 1234 plus 1234. So as we already said, we'll first enter the lower byte followed by the higher byte. So at location 3000, we'll store the value 3, 4, and at 3001, value 1, 2. Same is repeated for the second operand. 3, 4 at 3002 and 1, 2 at 3003. And we press escape again. Then we'll go for the execution mode. There I pressed G. They're asking me to enter the starting address of the program, which is 3000. Then on pressing enter, it will go into execution mode. Now, in order to bring the control back to the LCD screen, we'll press the reset button present. So we will be again diverted to the initial screen we had. So in order to check the result, we will give the option N and give the location of destination, which is 4000. And we will see that at the location 4000, the value is 0, which means there was no carry in the addition of 1234 and 1234. The result is 2468 and the carry is 0. So that is 0 here. Then at 4001, we will have the lower byte, which is 68, and at 4002, we have the higher byte, which is 24. And to escape this mode, we'll press the escape key. So we'll return to the initial screen. That's all for now. Thank you for watching.